Have you ever wondered about the mysteries that lie beyond the stars? Look no further. We're diving into the fascinating world of astrophysics today. The grandeur of the universe houses some of the most interesting phenomenons, one of which is the elusive black hole. These celestial bodies have been studied, predicted, and confirmed since the late 18th century, captivating the interest of humans on Earth. They are born from the collapse of immense gas clouds, implosions of colossal star cores, and even from collisions of neutron stars. But the most intriguing discovery about these enigmatic entities comes from the early 1970s. A brilliant physicist named Stephen Hawking proposed that black holes aren't eternal. They emit a unique type of radiation and eventually evaporate. This revelation, known as Hawking radiation, has sparked endless discussions and theories. However, there's a slight twist to this tale. According to physicist Ethan Siegel, the common explanation of Hawking radiation isn't exactly correct. The real explanation dives deep into the principles of quantum fields and the curvature of space-time. In fact, even the emptiness of space isn't truly empty. Intriguing, isn't it? But just when things start to get really interesting. Well, you'll have to wait and see. What's up, my amazing and curious folks? Ready to unravel the mysteries of the universe together? I'm your host, Caesar, and joining me is our brilliant commentator, Sonia. Don't forget to subscribe to the Curiosity Wonderland and hit that bell icon to get notified whenever we uncover a new curiosity.
Hi there, everyone. Can't wait to dive into today's fascinating topic with all of you.
Now, folks, let's dig a little deeper into our main theme today. Black holes, these fascinating and mysterious objects, have been on the scientific radar since the late 18th century. But they truly came into focus with the advent of Einstein's theory of general relativity in 1916. Can you believe that?
Really, that far back?
Indeed. And there are a variety of ways these astrophysical phenomena can form. They can be born from the collapse of gas clouds, from the implosion of the cores of stars, or even from the collision of two neutron stars. And we've observed them through numerous methods.
So they're not as elusive as we think, huh?
Not quite. They've been observed through electromagnetic emissions from surrounding matter, the motion of stars or binary companions around them, and even through the gravitational waves they emit when two of them merge. But here's where it gets really interesting. Back in the early 1970s, it was revealed that black holes can't last forever. They eventually evaporate due to a continuous spontaneous emission of radiation that emerges from them. This is known as Hawking radiation.
Wait, black holes evaporate? How?
Well, that's the million-dollar question, isn't it? Contrary to popular belief, it's not due to a cancellation of particle-and-antiparticle. Instead, it's the curvature gradient of the black hole that's responsible. But this may seem confusing, right?
Definitely. I mean, how can the bending of space-time result in radiation?
A fantastic question. To understand this, we need to start with empty space. We tend to think of empty space as a perfect void with absolutely nothing inside it. But from a physical perspective, that's not quite accurate. In fact, there's much more to empty space than meets the eye.
Really, like what?
We're just getting to the good part. Now, let's imagine the most isolated region of space we can think of, far, far away from any sources of matter. Even if you could shield a large volume of this region to keep everything out, electromagnetic fields, particles, radiation, there would still be something you couldn't remove.
And what would that be?
We can't extricate space itself from the laws of physics, right? So the fundamental quantum fields that are inherent to the universe will still exist. Even in their lowest energy state, with no excitations, these underlying fields still form a part of reality.
Wow, that's mind-boggling.
Indeed. Now these fields, which are the carriers of all fundamental forces, persist throughout all of space, whether there are sources present in that space or not. This brings us to the Heisenberg uncertainty principle.
Oh, I think I've heard of that one. It's about certain pairs of properties that can't be exactly measured together, right?
Exactly. For instance, position and momentum, energy and time, spin in perpendicular directions, and many others. It's often thought that if you consider a short enough timescale, then there will be a large associated energy that comes with it. And if this associated energy is large enough, then you could spontaneously create a particle-antiparticle pair of quantum particles from nothing.
From nothing? That's wild.
However, this is where things get complex. This depiction, despite its widespread use, is surprisingly inaccurate. The zero-point energy of empty space doesn't come from this particle-antiparticle popping. It's actually a complete fiction.
Really? So what's the real story?
The plot thickens. So what happens instead? Well, there is indeed something we call zero-point energy. It's energy that is inherent to the ground state of any quantum system, and it is typically positive and non-zero. But it doesn't originate from quantum fluctuations or quantum foam or particle-antiparticle pair popping or any other fancy term. It arises from the free Hamiltonian, representing a series of non-interacting quanta just existing, oscillating and propagating, but not interacting with anything else.
So there's no popping in and out of existence?
No, that's merely a calculational tool. These particles are virtual, not real. Quantum fields are permeating all of space, and there's no way to create a region devoid of them. You can be as far away as you want from all sources of matter and energy in the universe, but that doesn't mean you'll wind up in perfectly flat space. As long as we live in a universe that's expanding and/or has any sources of matter and/or energy anywhere within it, you can only approximate space as being flat and uncurved.
But space isn't actually flat.
In reality, there is some quantifiable, even if small, curvature to it. The amount that space-time is curved and distorted depends on how dense the object in question is. For a black hole, neutron star, white dwarf, or a star like our Sun, the spatial curvature is identical at sufficiently large distances. However, close to the event horizon of a black hole, more severe curvatures are achieved than anywhere else.
That's fascinating.
Indeed, it's a mind-boggling world out there. I'm always amazed at the vast universe of curiosities. So many discoveries, so many records, so many intriguing facts that defy our intuition. What do you think, dear listeners? Are you as captivated by these revelations as we are? Remember, we're here to learn and explore together, so don't hesitate to share your thoughts and questions. Do you find these tales of black holes and quantum fields as thrilling as we do? Don't forget to hit the like button if you're enjoying the journey so far. Let's continue diving deep into these mysteries. Shall we? Now remember, the key principle of relativity is that it only applies to inertial or non-accelerating frames of reference.
So if you're accelerating, your frame isn't as good as anyone else's, right?
Exactly. If you're in a rocket, accelerating through even flat, empty space, your frame of reference is no longer equivalent to others. Let's take a situation where you're not accelerating in flat, empty space. You'll merely experience an empty universe with no quanta of matter or radiation appearing in any direction.
Sounds serene.
But if you are accelerating, you'll experience what's known as the Unruh effect.
And what's that?
Well, you'll perceive a thermal bath of radiation, and the temperature of this radiation depends on the magnitude of your uniform acceleration.
So space isn't empty even when we're accelerating through it.
Right, you'll experience a bath of thermal radiation arising from quantum effects. The greater the magnitude of their acceleration, the greater the temperature of the radiation they will measure and experience.
So the faster you go, the hotter it gets?
In a way, yes. But it's not about speed, it's about acceleration. And all this happens due to the different state of the quantum vacuum that a stationary observer perceives as compared with an accelerating observer.
Space travel suddenly sounds a lot more complicated than just strapping on a rocket and blasting off.
It certainly is. But the beauty of understanding these principles is that they give us a deeper appreciation for the intricacies and marvels of our universe. This might blow your mind a bit, but even the tiny temperatures we're talking about are significant. If you accelerated at 1 g, like the gravity at Earth's surface, the Unruh temperature of your radiation is going to be about 4 times 10 to the negative 20th Kelvin, around 1 billion times smaller than the coldest temperature ever achieved in a lab.
Wow, that is mind-boggling.
Now we're going to take a massive leap from flat space into the curved space of general relativity. Einstein did this through what's known as the equivalence principle.
And what does that mean?
Let me explain. Imagine an observer in a room that's uniformly accelerating upwards, like an elevator being pulled up. Then imagine the same room at rest on Earth's surface, where gravity is pulling it down. If you dropped a ball directly downwards in both scenarios, what would be the difference?
They would act the same, right?
Absolutely. The two situations are physically identical. This key insight is what led Einstein to formulate his general theory of relativity, which replaced Newtonian gravity and is still our leading theory of gravity today.
That's fascinating.
Indeed. And this brings us to a curious question. If unruh radiation arises in empty space when we accelerate through it, what happens if we replace that acceleration with a source of gravity like a black hole?
That's a good question.
It's something that we're still exploring. But the key takeaway is that the nature of our universe is profoundly interconnected. Our understanding of these principles helps us better appreciate the incredible complexities and wonders of our universe. Consider the event horizon of a black hole. Both inside and outside this event horizon, space flows like a moving walkway or a waterfall. At the event horizon, you can't overcome the flow of space-time. It inevitably drags you into the singularity at the center. However, outside the event horizon, other forces can often overcome gravity's pull, causing even infalling matter to escape. This reminds me of a recent event.
Oh, what's that?
Well, I was reading about an experiment where scientists were attempting to simulate the conditions near a black hole. They used powerful magnetic fields to generate a flow of plasma that in some ways mimicked the flow of space-time near a black hole.
That's really interesting. Coincidentally, I was just reading about a similar experiment. In this one, scientists were using lasers to simulate the intense gravitational fields near a black hole. It's incredible how these experiments can give us a glimpse into such extreme environments, right?
Absolutely. They're our best way to understand these extreme conditions. In fact, as we get closer to a black hole, we accelerate more, and the black hole distorts space more. However, the more massive a black hole is, the larger its event horizon becomes. Therefore, the farther away from the black hole you have to be before you get swallowed up inside the event horizon.
So, the bigger the black hole, the safer you are in a way.
Well, safe isn't exactly the term I'd use when discussing black holes, but yes, you would have to be farther away to avoid being sucked in. Fascinating, isn't it? Let's dive deeper into black holes. They emit Hawking radiation, not Unruh radiation. This concept is named after the physicist Stephen Hawking.
The same Hawking who wrote A Brief History of Time?
Exactly. Although, interestingly, Hawking didn't mention the idea of particle-antiparticle pairs popping in and out of the quantum vacuum in his original paper. That analogy came later in his popular book.
I see. So what is the reality then?
Simply put, an accelerated observer, even in flat, empty space, will experience time differently than a stationary one. This difference in experience can lead to a thermal bath of radiation. This applies to any acceleration, whether due to a spacecraft, an elevator, or a black hole.
So this radiation doesn't require the presence of a black hole?
Not strictly, no. Even massive objects without an event horizon, like stars, may emit some amount of Hawking radiation.
Fascinating. But what are the debates about Hawking radiation currently?
Mainly, it's whether we'll ever be able to measure it, and whether it requires an event horizon to exist, or whether all masses create it.
And this connects to the dark, energy-rich, expanding universe and the period of cosmic inflation that set up and preceded the Big Bang.
In a sense, yes. The zero-point energy of space has some finite, tiny positive value, which is one way to talk about dark energy, as a form of energy inherent to space itself. It's all deeply interconnected. Let's wrap up our journey on this topic with the presence and properties of dark energy in our universe. Because of dark energy, we find a continuous amount of thermal radiation from the perspective of any stationary observer. Even far into the future, this implies that our universe will always be filled with a tiny amount of blackbody radiation, peaking with a rather minuscule temperature of about 10 to the power of -30 degrees Kelvin.
Wow, that's incredibly cold.
Yes, it's quite something to ponder. But remember that early on, space was also filled with a form of energy inherent to it, albeit of a much greater magnitude during the period of cosmic inflation. Although we don't yet know the energy scale of inflation, we can expect much greater temperatures from that more rapidly expanding phase. We're talking around 100 degrees Kelvin, which would be warm enough to boil liquid nitrogen away.
It's fascinating to consider how different our universe was in its early stages.
Absolutely. And that's not all. The expanding universe doesn't create an event horizon like a black hole does, but a cosmological horizon. This means that we can be confident this radiation will be real, as long as space-time is bent in such a way that objects accelerate through it. And because the acceleration changes closer to or farther from a source of mass, radiation will propagate from regions of stronger curvature to regions of weaker curvature. It's a little more complex than Hawking's oversimplified picture of particle-antiparticle pairs, but it's a more correct explanation. So, we've journeyed through the fascinating world of black holes, debunking some myths and shedding light on the nature of Hawking radiation. We've moved away from the common belief that radiation is caused by particle-antiparticle pair popping and ventured into the principles of quantum fields and space-time curvature. The challenging adventure through empty space, the Unruh effect, and the continuous emission of radiation from our expanding universe has truly been an enlightening expedition.
Absolutely. We've unraveled the true essence of Hawking radiation, deepened our understanding of black holes and the fundamental properties of space-time. It's like discovering an unexpected twist in a cosmic thriller.
And remember, just like the unexpected science behind the black holes, life's most profound secrets often lay hidden beneath the surface. So keep exploring.
Couldn't agree more. Thank you all for joining us in this cosmic journey. If you loved this episode, don't forget to blast that like button, drop your thoughts in the comments, and share the episode with your friends. Let's spread this cosmic knowledge far and wide.
Until next time, keep your curiosity alive and your mind open. Goodbye, everyone.
Goodbye, stay curious, and keep exploring.
This fascinating dive into Hawking radiation was inspired by an article titled Ask Ethan, How Does Hawking Radiation Really Work? By Ethan Siegel, published on Big Think on February 9th, 2024. If you want to delve deeper into the subject, the full URL is in the video description. Until next time.